Hello, I'm Zhana, and here we want to prove this theorem 7. If A is an n by a matrix, then A, the null space of A, and the row space of A are orthogonal complements in Rm with respect to the standard Euclidean inner product. And B, the null space of A transpose and the column space of A are orthogonal complements in Rn with respect to the standard Euclidean inner product. So A point first. So we want to prove that the null space of A okay, and the row space of A are the orthogonal complements. So we can write it as the null space of A equals to the orthogonal complements to row space of A. So first, okay, we want to prove that if we let X denotes a vector in orthogonal complements to row space of A, then we have that AX equals to row vector 1 of A, row vector 2 of A, and so on until row vector, because A have n row, then we can write it so on until Rn, row vector n of matrix A. And then times x1, x2, and so on until xm, because each of row in matrix A has m column, so that's why we times it with vector x that has m dimension. Yeah. And AX will be equals to R1 dot product X, R2 dot product X, and so on until Rn dot product X. Because each of this row, for example, R1, each of the entries in R1, we multiply it with each of these entries of vector x, and then we add them, and that's why we can write it as the inner product of the standard Euclidean. So that's why we can write it as the dot product. And because of this vector x is the orthogonal complement to row space of A, that means that X will be orthogonal with each row of matrix A, and that's why the inner product of R1 dot X will be 0, and R2 dot X will also be 0, and so on until Rn dot X will be 0. Thus, we can say that X is in the null space of A. And then let X is in null space of A. Then it will satisfies the equation ax equals to zeros vector, which means x is in the orthogonal complement to row space of A. So because A times x equals to zeros vector, that means that each of row in matrix A, each of row of matrix A, the inner product of that each of rows of matrix A with vector x, that will be 0. That means that each of row of matrix A will be the orthogonal of vector x, and because all of these row in matrix A is orthogonal with vector x, then x will be the orthogonal complement of row space of matrix A. And therefore, we have row A. Okay, we have the orthogonal complement to row space of A equals to null space of A. Next, we want to prove the point B. So we want to prove that the null space of A transpose equals to the orthogonal complement of column space of A. Okay. First, let X denotes a vector in orthogonal complement to column space of matrix A, and C1, C2 until Cm are the column vector of matrix A. Then we have A transpose times X equals to C1, C2, and so on until Cm times x1, x2, and so on until xn. Okay, so A is matrix n by m. So that means that the number of column is m and the number of row is n. So the dimension of x will be n. Okay, so because for each entries of C1, C2, and so on until Cm, so for each of this entry, we multiply it with x1, x2, and so on until xn, and then we add them. We can write it as C1 dot x, C2 dot x, and so on until Cm dot x. And because we have that x is denote a vector in orthogonal complement of two column space of A, that means that X orthogonal with each of the column vector of A. So that means that the inner product of C1 dot X will be 0, C2 dot X will be 0, and so on until Cm will be 0. And that means that X is in no space of A transpose. And then that let X is in null space of A transpose. That means that it is satisfied that A transpose X equals to zeros vector, which means that X is in the orthogonal complement of row orthogonal complement to row A transpose. Or we can say that because the row spaces of A transpose is column of A, we can say that the orthogonal complement of two row space of A transpose is the orthogonal complement of column A, column space of A. So therefore, the null space of A transpose will equals to the orthogonal complement to column space of A. And that's the two proof for each of the point in Theorem 7. Thanks so much.